is a graphic illustration of the concept, why it works, and how you can chart. Now, some of you know that when we have a failure, there are some gurus that are sometimes brought in, and they say, well, this failure initiated at this point. Well, how do they know that? Well, you know it by looking at the growth. First of all, the initiation point and the way the crack grew, you can chart back to the point at which the event was initiated. And it isn't always just a crack, but this is a good graphic illustration of that. So that's the way it's done, and all of you need to be aware of that. Now, the other thing you need to be aware of is if I inspect right after it's gone through one of those overloads, that crack is going to be very tight. And I'm going to have difficulty detecting that crack, even though it's within the range that I normally would expect to see it. And secondly, if I inspect at that point and I'm trying to go back to size it, as is done quite often in the nuclear industry, I'm always going to size it wrong, because the crack form or the crack characteristics have been modified by the event and by the load, the compressive load that is on there. Now, if I take a crack, initiate a crack, you expect the crack to grow in this kind of a shape. Now, if I overload that crack, what's going to happen is I'm going to close the mouth of that crack, and I may actually close it further. And so such things as liquid penetrant, which are a mainstay of what we do in a lot of cases, are minimally applicable. So the state in which the part has been used is important. That's the reason why in aircraft maintenance we sometimes jack up the wing to put reverse stress and try to open up the cracks. It's not a very effective way to do it, but it's better than letting it be inspected in a drooped condition. So there are many things that go along with that. Now, in terms of the requirements, what we require as NDT guys is not an easy task for the designer. So I must know the type of defect that I'm looking for. I must know the size of it. I must know the location. I must know the orientation. And I must know the nearest neighbor, and that is the proximity of one crack to the next crack. And that's the basis for all acceptance criteria before you come to the NDT guy. You must know the answers to these problems. The good news is that all parts are not fracture critical. So I don't have to inspect everything 100% with the smallest crack detection device that I have. And all areas within a given part are not fracture critical. So it's necessary to define and to locate. There's a lot of misunderstanding on that, and within the aircraft or aircraft engine community, one of the notable engine builders said, well, we know how cracks initiate and grow, and we can put a crack size on there. And what we will do is put an EDM slot in there, start the crack, and grow the crack. And so inherently, the crack was put at the center point in the radius of a stiffened structure. In nature, that's not where the crack grows. The crack initiates and grows at the tangency point of that radius. And so much of the work that had been done in lifing that particular engine had to be done over again because of an assumption It was not validated before we started the calculations. Now, I put this in there because you folks that are in the solid rock explorer community know how important that is. We have different kinds of flaws. The location of the flaw is critically important. The type of flaw is critically important. Nearest neighbor is critically important. So this illustrates all of the things that I am talking about. Now, see, we have at least one person here from Field. We built, before I retired, we built a automatic CT image system for the inspection called a rock motor component field. And this is the philosophy that we used, the philosophy we tested before that went into production. As far as I know, that went out of production, or that unit went out of production as it was replaced about 3 years ago. Is that about right? It had been refurbed, but the interesting part was that some of the software was reused because the new software didn't work, and it was reused, and this was one of the baselines. We had to assume these things to go through and come up with the acceptance criteria that we were able to work with. Now, within the NASA community, as I say, NASA was one of the pioneers in this area. There are some articles that they declare as being fracture critical by nature, and pressure vessels being one of them. Any large part that has a lot of inertia can come apart and destroy the system. Or the third bullet there is any component whose failure would cause loss of life and mission by damage to other areas. Any single load path, single function materials such as components and heat shields, that there's no backup system. And the bottom line is anything that could be shown to potentially cause loss of life or mission. Now, with that introduction into the NASA program, we were approached by NASA in the late 60s to perform a program to support what we were doing in Space Shuttle for fracture analysis and prediction of the mission. And with that, we had done some work in the laboratory prior to that in detectability. And keep in mind that NDT guys never start to be NDTers. They're always coming from some other community. And the majority of NDTers are either mechanical engineers or physicists. But I don't think like either one of those. I was trained initially as a chemical engineer and then did my graduate work in biophysical chemistry. So I think in terms of the end-to-end process, the task that we were asked to do was to create a number of cracks in aluminum alloys that would be used for Space Shuttle and to perform inspections on those and to document those inspections. Now, we started we generated 118 panels containing two different thicknesses, 60 and 210. There were 328 cracks in that set. They were inspected by 3 different experienced inspectors in the as machine condition, after etching, and after proof loading. They were inspected by X-radiography, accurate, ultrasonic, and fluorescent penetrant, and this was early 70s, so some of those techniques have improved. And later we added holographic inspection, and we also did acoustic emission because all of these parts were pulled to failure and the physical crack size measured. So we not only knew that the crack was there, we knew what its physical dimensions were, and that was the program. And for those of you who are near, one of my tie jacks is one of those original cracks from that program.